Welcome back, future pilots. Today we begin your journey into meteorology with a look at the invisible force you'll fly through every time you take off, the atmosphere. It's not just empty space. It's a living system that shapes flight, weather, and even your aircraft's performance. The atmosphere surrounds Earth like a giant ocean of gases. It provides air to breathe, weather to plan for, and the very lift that keeps aircraft in the sky. Understanding its structure and behavior is one of the most valuable tools a pilot can have. Let's start with structure. The atmosphere is divided into four main layers based on how temperature changes with altitude: the troposphere, stratosphere, mesosphere, and thermosphere. Each layer behaves differently and affects flying conditions in unique ways. The troposphere is the lowest layer. It extends from the surface up to about 36,000 feet, depending on where you are and the season. It's here that all weather occurs: clouds, rain, wind, storms, and turbulence. That's why most of your flying will happen here. Temperature decreases as you climb through the troposphere, typically at a standard lapse rate of 2 degrees Celsius per 1,000 feet. That drop in temperature affects how your engine performs, how the air carries your wings, and even how long your takeoff roll might be. Above the troposphere lies the stratosphere. It's more stable and much drier, with little to no weather activity. Many commercial jets cruise in the lower stratosphere to avoid turbulence and maximize fuel efficiency. It also contains the important ozone layer. Interestingly, in the stratosphere, temperature begins to increase with altitude due to absorption of solar radiation by ozone. That's the opposite of what happens in the troposphere, and it plays a role in aircraft performance and the physics of jet stream winds. Higher up, we find the mesosphere and thermosphere. Aircraft rarely fly here, but they're important for understanding Earth's energy balance and atmospheric phenomena like auroras. Temperatures in these layers can be extreme, especially in the thermosphere due to solar activity. Now let's talk about what the atmosphere is made of. It's mostly nitrogen, 78%, and oxygen, 21%, with small amounts of argon, carbon dioxide, and water vapor. This mix affects air density, which impacts lift, drag, and engine power at all altitudes. Water vapor, or humidity, plays a surprising role. More humidity actually means less dense air. That's because water vapor is lighter than nitrogen and oxygen molecules. Less density means reduced lift and engine performance, especially important during takeoff on hot, humid days. Now consider pressure. At sea level, standard atmospheric pressure is 1013.25 HPa or 29.92 nhg. As you climb, pressure drops because there's less air above you. This is why aircraft instruments, especially altimeters, must be adjusted to reflect local pressure. Altimeters measure pressure to indicate altitude. If you don't set the correct pressure, called QNH, your altimeter may show the wrong height. That can be dangerous when flying near terrain or during approach. Always confirm and update pressure settings as needed. Let's explore QNH, QFE, and standard settings. QNH sets your altimeter to read elevation above sea level. QFE sets it to show height above a specific airfield. Standard pressure, 1013.25 HPa, is used above transition altitude for uniform flight level separation. Now let's connect pressure to air density. When pressure drops, so does air density. Lower density means reduced lift, lower thrust, and longer takeoff distances. That's why hot and high airports are more challenging for pilots, and why performance calculations are critical. Performance charts take into account temperature, pressure, and humidity to help you determine safe takeoff and landing speeds. Ignoring density altitude can lead to sluggish climbs, reduced climb rates, or even an inability to clear obstacles after departure. Temperature is also a major factor. Cold air is denser and gives better engine power and lift. But it also increases the risk of icing, especially in moist conditions. Understanding how temperature changes with altitude helps you prepare for these challenges. The atmosphere also generates wind. Wind is caused by pressure differences between regions. Air flows from high pressure to low pressure areas, but it doesn't go in a straight line. Earth's rotation introduces a twist, the Coriolis effect, which curves winds globally. In the northern hemisphere, wind curves to the right. In the southern, it curves to the left. This creates major systems like the jet stream, trade winds, and cyclones. As a pilot, understanding wind behavior helps you interpret forecasts and anticipate turbulence. Winds near the surface are influenced by friction with terrain and obstacles. They are often slower and more variable than winds aloft. Knowing the difference helps you plan for landings, takeoffs, and possible crosswinds that affect aircraft control. At altitude, wind is faster and more stable. Upper-level winds can greatly affect fuel consumption, ground speed, and comfort. Headwinds reduce range, while tailwinds increase efficiency. Jet streams and narrow bands are very fast when found at cruising altitudes. Understanding wind helps you choose the best runway, anticipate drift during cruise, and stay safe during approach and landing. Crosswinds, wind shear, and tailwinds all behave differently, and the atmosphere gives you clues if you know how to read them. Let's talk about visibility. The atmosphere contains particles like dust, smoke, and moisture that scatter light. This affects how far you can see, especially in fog, haze, or rain. Pilots rely on visibility for VFR navigation and safe landings. Clouds are another key feature. They form when air cools to its dew point, causing water vapor to condense. Different cloud types indicate different weather. Knowing what each one means helps you anticipate turbulence, icing, and precipitation before you encounter it. The atmosphere also plays a role in turbulence. Air moving over mountains, through jet streams, or along weather fronts can become unstable. Pilots must recognize signs of turbulence, adjust altitude when possible, and prepare passengers and crew for a smoother ride. Icing is a major hazard. In visible moisture and temperatures below freezing, supercooled water droplets can freeze on contact with aircraft surfaces. This disrupts airflow and adds weight. The atmosphere provides the perfect conditions. You just need to know where to look. Aircraft systems can combat icing, but the best defense is awareness. Understanding cloud types, freezing levels, and moisture conditions will help you avoid the worst of it. The more you know about how the atmosphere behaves, the better you'll manage risk. Let's shift back to atmospheric layers. The tropopause is the boundary between the troposphere and the stratosphere. It's marked by a sudden stop in temperature drop. It also acts like a cap, trapping weather below and marking the top of turbulence zones. Jet streams often flow just below the tropopause. These high-speed winds can reach over 200 knots and greatly affect long-range flight planning. Flying with a jet stream can save time and fuel. Flying against one can make a flight drag on forever. The more you understand the structure and behavior of the atmosphere, the better prepared you'll be as a pilot. It affects everything: engine power, lift, drag, navigation, and even your health. You're not flying through nothing, you're flying through science. As you study aviation weather and flight performance, remember that everything connects back to the atmosphere. Every forecast, every checklist, Every graph in your performance manual is based on how this system works. It's your classroom in the sky. The atmosphere isn't static. It changes hour by hour, region by region. Learning to recognize patterns, like the buildup of storms, shifts in pressure, or changes in humidity, gives you a tactical advantage every time you plan and execute a flight. Even when you're not flying, watch the sky. See how clouds form, how winds change, how visibility drops at dusk. Pilots learn from books, but they master flying by observation and experience, and the atmosphere is your constant teacher. To fly safely and confidently, you need more than just stick and rudder skills. You need environmental awareness. Every takeoff and every landing is shaped by conditions you can't see, unless you know how to interpret the signs around you. From pre-flight weather briefings to in-flight adjustments, your decisions will always be guided by how well you understand the atmosphere. This knowledge is what separates an average pilot from an excellent one. And it starts with the basics. In the next lesson, we'll zoom in on one of the most critical elements of the atmosphere, pressure. You'll learn how it's measured, how it changes with altitude, and why it affects instruments, performance, and weather forecasting. Thanks for watching this introduction to the atmosphere. Keep this knowledge close. It's the foundation of smart flying. Now get ready for Meteorology number 02, Pressure, Part 1, where we'll go even deeper. See you in the skies.